When confronting a complex physical system in motion, the true barrier to solving it is rarely the mathematics itself. The primary hurdle is translation, is naturally drawn to physical attributes. We look at the container's mass, the material of the ropes, and conditions of the environment. In physics, these surface-level details clutter the path to a solution. Newton's second law, force equals mass times acceleration, functions as a strict operating protocol. To output an object's acceleration, the equation demands a specific, sanitized input, the net sum of all forces acting upon it. We generate that input using a free body diagram. It strips away the physical environment entirely, reducing an object to a dimensionless point at the center of a coordinate grid, leaving only external force vectors. By adhering to a strict modeling algorithm, we can scale our problem-solving from an inert object sitting on a desk to a ballistic projectile experiencing variable atmospheric drag. We begin testing this algorithm with a system in static equilibrium, a traffic light suspended by two distinct wires. The first step is to define the system of interest. This creates a strict boundary, isolating the object from its surroundings. Once the boundary is drawn, the only forces that matter to our equation are the external forces physically crossing that line. Step 2 discards the physical context, leaving only a point mass on a grid. Step 3 identifies a downward weight vector and two upward tension vectors. Finally, Step 4 projects these forces onto orthogonal x and y axes using sine and cosine functions. Finally, Step 5 applies Newton's second law. Because the traffic light is static, its acceleration is 0. Consequently, the net force along the x-axis must equal 0, and the net force along the y-axis must equal 0. By following this algorithm, the free body diagram has taken a three-dimensional engineering scenario and successfully converted it into a basic system of linear algebraic equations. The algorithm faces a more demanding test in dynamic frames, where uniform acceleration breaks the equilibrium along our axes. Consider a classic physics problem, calculating a person's apparent weight when they stand on a bathroom scale inside a rapidly accelerating elevator. We start by defining the system of interest, drawing a strict boundary around the person. A common misconception is that a scale measures gravity. It actually measures the normal force. In this free body diagram, the normal force pushes up, while gravity pulls down. Applying Newton's second law here, the equation is unbalanced. Upward normal force minus downward weight equals mass times upward acceleration. Rearranging the equation to solve for the normal force reveals that it equals mass times acceleration plus mass times gravity. As the elevator accelerates upward, the normal force must increase to accommodate the extra force required to move the mass. The sensation of feeling heavier as an elevator rises happens because the normal force must overcome your resting weight to produce that upward acceleration. We escalate the complexity further by looking at a coupled system. An Atwood machine suspends two objects of different masses over a pulley, meaning the movement of one object directly dictates the motion of the other. The instinct here is to model the entire machine as a single system of interest. Attempting this breaks the internal logic of the math, because the parts are accelerating in opposite directions. Instead, we draw two separate free body diagrams. For the first mass, a tension vector points up and a smaller weight vector points down, resulting in upward acceleration. For the second mass, the same upward tension fights a much larger downward weight vector. These two isolated diagrams are linked by a kinematic constraint. A kinematic constraint is a physical restriction on a system's motion. Because the masses are connected by a physical string, the tension force and acceleration magnitude must be shared between the two sets of equations. Coupled physical objects do not break the fundamental modeling rules. They simply provide a shared mathematical variable, allowing us to link independent equations together to solve the larger system. Introductory physics often assumes constant forces, but reality is frequently variable, requiring us to account for changes in the forces themselves. A baggage tractor progressively throttling its engine to haul heavy carts generates a force that changes continuously over time. Alternatively, a mortar shell fired straight up into the air encounters an atmospheric drag force that scales exponentially with its speed. Confronted with variable forces, the Newtonian algorithm holds. The core equation, force equals mass times acceleration, simply transforms from basic algebra into a differential equation. If a force is time-dependent, we rewrite the equation. We replace the fixed acceleration variable with its calculus definition, the derivative of velocity with respect to time. We then integrate the function across the specific time interval. For a velocity-dependent drag force, we apply the chain rule, replacing acceleration with velocity times the derivative of velocity with respect to position. We then separate the variables, isolating velocity and position terms, and integrate both sides to find maximum height. Applying calculus allows the free body diagram to track forces as they evolve second by second. We have tested the mechanics algorithm across 3 levels: the static algebra of the traffic light, the linear systems of the Atwood machine, and the variable force calculus of the mortar shell. The underlying realization is that the complexity of a physics problem has almost nothing to do with the physical object itself. The difficulty is entirely dictated by the mathematical behavior of the forces crossing the designated boundary of your system. Despite the wildly different conditions, the bridge between the messy physical world and the precise mathematical solution is always the exact same procedure. No matter how chaotic a physical system appears, the methodology holds. Define the boundary, isolate the system, and trust the algorithm.